That's a controversial session. Morning session has to be controversial to wake everyone up, so bear with me. So first of all, to thank EPSRC. So the work I'm going to be talking about, almost all of it was done thanks to this EPSRC grant, which is now running to a close. And I've structured the talk in three questions. The first one is why and what do we verify when we deal with neural networks? So the first elephant in the room is that, of course, everyone is now plugging in neural networks everywhere. In perception units in autonomous cars, in smartphones, within robots, in aircraft controllers, and many more. And in principle, you say you need some safety, security, robustness guarantees about them. This is ironic because yesterday we heard a talk from June and Cell 4, where all of this stuff was put in this box saying it's unsafe and untrusted, and you then package this inside of Cell 4 and say, okay, so just isolate bad stuff and then verify everything that's good. So we're talking in terms of June's talk yesterday, we're talking about that bad corner, like bodies. What do you do with them? So the main question, I'd be very happy if at the end of this talk, you will all have your own opinion about this question. Why very clever people like June don't want to deal with bad stuff? Why is it bad stuff even? Will it ever be good stuff or even like gray stuff rather than bad stuff? So if we can come up with conclusion, what is wrong? Is it fundamentally wrong, or is it just now it's wrong, it's coincidentally wrong? That would be a great achievement of this talk. And by the way, the neural network is just a function with vectors as inputs, vectors as outputs. What you see as nodes is in fact just a bunch of tensor operations. Well, what else to say? You will sometimes see this theta. It just says that there are some parameters here in these tensor operations that are optimized, so they're not given in advance. But once your optimization process finished, you're gonna get a neural network where this theta is fixed. Right, so it would have been nice, it would have not been a bad stuff if we could have the following scenario. You have an image somewhere there, you have your autonomous car with a perception unit, it processes the image, gets it through the neural network, and recognizes where it sees pedestrians, and then it gives you a correct decision whether you should stop, go right, left, or whatever. So the dream property would be to verify is that the autonomous car never runs over pedestrians. But however, there is no formal characterization of what an image of pedestrian even is. And of course, lack of formal definition of inputs prevents from formulating interesting safety properties. So that is the first reason why people like June don't want to deal with this part of neural net verifications. To summarize really all the problems that we know with neural net verification, we'll have to maybe go through this slide. In the standard, what we call classical problems, you have the situation when you have a good specification, or at least explicit specification, whether it's good or bad, and usually low-dimensional inputs. In neural networks, you have high-dimensional input and not specification. Well, I could say data is a partial specification, but is it really? Then you have programs, actually, with large specification. Who is writing programs? Most likely it's going to be a human being writing a program. In case of obtaining a neural network through optimizing these parameters theta, and that's the loss function that you're optimizing, well, it's kind of coming up with this final program, which is a neural net program as a function. But really, it's an indirect writing of programs through minimizing some sort of objective function. And finally, coming to verification, you have a lot of good tools to do program verification for standard programs, and you have some experimental verifiers here in this corner. So if you're a June or any other person who does real verification, your conclusion is probably ending here. I better stay with the standard verification and never touch neural network verification. So these are the two problems that I wanted to put forward immediately to recognize where we are in this area, and this is the elephant in the room. And now we're gonna, having acknowledged all the problems and that the area is in the early stage, we wanna look a little bit deeper at what's going on there in order to decide, will it ever stay the same? So let's look closer, actually, what happens there and what sort of things people try to verify. There was a paper in 2014, quite famous, that discovered that, well, you can perturb, you can have an image which is recognized with 97% confidence that it's a red light. You can add a bit of noise, which as a human you wouldn't even notice because that's the resulting image after noise. And suddenly you can make a neural network, say neural network that thought that this is red would tell you that's green. So that's famous notion of adversarial attack. And if your neural network doesn't fall for this, it's adversarially robust. In 2014, well, 10 years ago now, machine learning community have gone through all of these stages. They realized that, first of all, these attacks transfer from one neural network to another. So if I learned to attack my neural network, I can attack yours. They affect any domain where neural nets are applied. Large language models, for example, could also be attacked. And this is not sort of problem that you can eliminate by simply increasing network size or changing architecture, changing exploration functions. It is funny, really, why this came as such a big surprise. So neural networks were roughly suggested in 1943. In the 90s, we had the rise of machine learning applications. No one noticed anything until this paper, well, 2013, same paper, is just, I think it got to archive 1 year earlier. And now they've got this surprise about this adversarial robustness. In this paper, they say the existence of adversarial negatives appears to be in contradiction with network's ability to achieve high generalization performance. Indeed, if the network can generalize well, how can it be confused by these adversarial negatives? And then, of course, in the machine learning community, that gave rise to tens of thousands of papers of people trying to train neural networks that are more robust. All of this in kind of attack defense style. When I saw this for the first time, I thought, why even they're surprised, right? We knew that neural networks can be inaccurate. What's so surprising about this? The surprising thing about this is that this violates a specification that machine learning community had all along. They don't mind if the neural network misrecognizes certain input from data. But they had this specification in their head that if my neural network can deal with this example, and I perturb it by 1 pixel, it shouldn't change its classification. So it wasn't specification about data. It was your specification about the behavior of your models, which was implicit, and machine learning community didn't really realize this. So that's why it was so intriguing for machine learning. And this is my first claim, that robustness is an example of a desirable property or spec that neural networks cannot learn from data. It's not something that is inferable from data. And it was intriguing 10 years ago because that was the first time when machine learning community came face to face with the notion of specification. Let me prove this point and actually show that it's proper mathematical specification. You want to define, first of all, something that in machine learning and neural net verification is known as notion of an epsilon ball. So suppose this image of 7 is actually from your data set. And then you say, well, and this is a multidimensional vector space. And I'm saying, well, I'm drawing an epsilon ball around my 7 from the data set. And I want to say that my spec needs to say that anything that falls, all the infinity of images that falls within this epsilon ball in the real vector space should be classified robustly. So data is given here only by 1 point, and everything else is just concerning all vectors within the vicinity in this generality. Well, when we had a look at that, we noticed that there are quite a few notions of what robust even means. So for any x in your epsilon ball, you want output of the neural network to be robust, and there are quite a few definitions what robustness meant. And by the way, for those who like types, of course, robustness as a property is also a refinement type because you are defining the type of inputs, which are real vectors, and the types of outputs, which are also real vectors. All right, so this was interesting for us when we started way back in 2022 to find that, and machine learning community, by the way, sometimes they explicitly understood that they were optimizing for one of those options, and sometimes it just happened that they optimized for a certain notion of robustness without actually stating this in any explicit way. All right, so that is as much as we have background on machine learning robustness. And of course, after machine learning brought this example, a verification community responded to this. And in 2017, in CAP, there were 2 papers on neural net verification, one by Guy Katz and his group and Clark Barrett, and the other is by Marta Kwiatkowska from Oxford. So a couple of papers appeared, and since then there have been hundreds of papers on neural net verification. Not quite thousands, no, so this community is much larger than verification community. So a few words of what actually happened here on the verification side. There are about a dozen of different neural net verifiers, and they're all based on slightly different technology, SMT, abstract interpretation, interval arithmetic, linear bound propagation. There are international standards and competitions in this field, similar to, if you know SMT solving community as an SMT-lib format and competitions in that domain. So that was closely modeled on that. And the one that we're going to be referring to today would be Marabou, the first on the list. So that's a development of the first paper in 2017 by Clark Barrett and Guy Katz, and it just got a new edition in 2024. All right, so, well, this was a crash course for you on neural network robustness and verification. And the question number 2, what do programming languages have to do with any of this? And it's not obvious from the little introduction I gave that neural network verification is a programming language challenge. Well, let me try to maybe persuade you a little bit about this. So when we looked into this, we found approximately what I've just told you. There was some work on neural net verification, some on training. And roughly, it could be summarized like this. So machine learning people had in mind some vague understanding of what robustness is, sometimes not vague, sometimes vague. They somehow managed to express it as optimization objective. They did neural network training, and of course that training was implemented somewhere in Python. Neural network verification people also had a property in mind. Perhaps they thought that that's the same as those people have in mind. Well, what would they do? They would have their verifiers here, Marabou or other. They would also need to take this implementation from machine learning people, convert it into a representation that's good for an SMT solver. This is called ONNX, Open Neural Network Exchange format. And then they would feed their verifier with the property and with this implementation, which we think is equivalent to this. As you can see, it would have been lovely if this was a commutative diagram. To make it commutative, you need to have a solid arrow here, which doesn't exist, and a solid arrow back, and maybe fix a few. Fortunately, not quite a commutative diagram, and that's actually is the problem. So let me walk you through different parts of this diagram and tell you about different problems that we encountered. So the first one, as mentioned, was that although both sides thought that they were optimizing and verifying the same property, it turned out that there was a lot of confusion in how people understood what their property is here and what they verify for in here. In this paper, we just showed a few bugs in the literature when someone, for example, used data augmentation. You use data augmentation, you in fact optimize for classification robustness, but then that person got this neural network and verified this for standard robustness, for example. More importantly, we show that these different types of robustness are not interchangeable. If you optimize for one, you're not necessarily improving the other. So you actually need to know what you're doing. So this was kind of a problematic corner. Lack of clarity as to actually what property is being propagated here, and lack of any formal connection between optimization property and verification property. That was the first time when we thought maybe it's actually a programming language problem. Would be nice, we thought, to have some sort of external specification here that would control optimization and verification somehow, so that you state property once, you declare it clearly, formally, And then you compile down this to optimization and verification, and at least you have one source of truth about what actually is the specification. But before I go for this, you may ask me, hey, maybe you would be happy with just this specification language that the SMT community came up with. Maybe you don't need to build up this strange pyramid. And yes, we tried. We thought maybe already someone has come up with a very good specification language. This is literally how neural network robustness is defined in VNN-lib, which is a standard format for neural net verification. So this is copy-pasted from competition this year, except for I curtailed here x1 to x791, etc. So, but other than that, it's a complete file. Well, you could tell me what's wrong with it. You're probably a bit bewildered. Well, first of all, do you see a neural network anywhere? Do you see real vectors anywhere? Can you actually, I mean, what would make you think it's a robustness of neural network specification at all? Yeah, so it's problematic. There is lack of expressivity. I'd like to be talking about in my specification language about neural network inputs, output, etc. Lack of conciseness. Instead of talking about vectors, I have to talk about every vector element for some reason. Lack of rigor. This specification language has no formal semantics. In fact, there is no specification at all what VNN-lib as a language allows you to do in its syntax. There's no dynamic bindings to data sets. I presume you want to be talking about examples from data sets around which you build epsilon balls. A neural network is defined in a separate ONNX file. So you actually have two files to run, this one and another one. But this is, of course, a source of bugs, right? If you define neural network elsewhere, then you put this all together, kind of heat it up and cook. So we found that this specification language is a source of bugs. And bugs occur even in specs that are recognized benchmark in the community. So we said, no, we're not going to use that specification language. So we came up with our own. So that's language vehicle that we created within this grant. This is epsilon ball robustness specification. I don't really want you to read the whole of it, but I want you to just say that and if you wanted to write clean specifications, there'll be a few things you want to say. You want to say what is the type of your inputs and outputs. As types, you want to have tensors of some size. You want to have a definition of, even if you do use ONNX format somewhere, you at the very least would like to say what the type of your neural network is, what valid images and invalid images are. You want to have a binding to a data set because that's where you're going to be taking your images from. Well, and here's your robustness property. So this is just a tiny, clean language in which at least you can have some order and full specification of the problem. And I wanted to also say that at the same time as we were thinking about this, there was a group in France that came up with the same idea that they absolutely cannot have VNN-lib as a specification language, and that they came up with their own specification language. So hello to you from Julien Gérard-Setaban in France. Anyway, just to say we were not the only ones, and this is a sensible idea. Can I take the questions at the end? You wanted? Okay. There was another thing that this specification language allowed us to solve. What we noticed was the problem is that very often neural networks are part of bigger systems. No one is interested in neural networks on their own. And when people specify these neural network systems, they say, okay, neural network will be this controller in the airplane. And if it's given, its inputs will be given maybe in terms of speed, angles, distances, and under these certain conditions, it should tell me clear of conflict, turn right and turn left. When people in the verification community were verifying these sort of specifications that actually had some physical parameters, they were normalizing them over, and neural networks here only saw some normalized values between 0 and 1, whereas specification here could have kilometers, miles per hour, or something like this. So we call this the embedding gap, because the neural network you're actually verifying had no idea about physical parameters of the system that were specified by engineers who actually gave you the spec. And our specification language allowed us to clearly state how we convert, how we normalize the values, and what was the original specification. So vehicle as a language is really just a specification language. It has types. It will tell you if you messed up with types of your neural networks or data. And it could be compiled to 3 backends: for training, for optimization, and give you loss function, to the Marabou tool for verification, or to integration with larger system properties, which we implemented in Agda. I want to also finish with that problem, which we didn't look too closely into, but there's another group in Manchester by Lucas Caldeira and Eduardo Manino that looked into this problem. I told you that you were taking a regional neural net implementation and then verifying its ONNX format, which is a representation format. They found that there are lots of murky business happening in this side as well. That basically, when you verify something here, your verification guarantees did not actually extend to your original neural network. And the list of reasons why takes the whole page. There's, of course, the problem that here ONNX assumes real numbers, and your verifier takes real numbers, real vectors. This one takes floating points, so there's discrepancy there. But there are other things. There's non-associativity of floating point operations here. So unless you know the sequence of operations when you verify something, you're actually not guaranteed to get the result. And other things, there's auto-selection of optimization primitives, runtime optimizations, non-deterministic training parameters, all sort of stuff that makes a good machine learning library good, that you completely lose by the time you verify it. And depending on all these choices that sometimes happen without you even knowing it, you're actually getting very different neural networks here, whereas you only statically verify one of them on that side. So that's not a good thing either. So we got now to the picture how machine learning and verification community build some kind of verification pipeline in a way that almost every bit of it is broken. And in principle, programming language community could have helped by taking this and building this on top of a good specification language. So what is next for this area? Well, take home lesson 1. Well, all mistakes and teething issues that standard software verification could have with implementation issues, with specification issues, can happen and do happen in neural net verification. For example, the strange VNN leap specification language is essentially SMT leap specification language. It wasn't given by aliens. It's actually coming from standard verification. Neural net verification, unlike the standard verification, has many backends. There is optimization, solving, refinement types of specifications, complex implementation regimes, which potentially demand even more non-trivial programming language support than you needed if you just had an SMT solver and some small C program. And if you actually ignore it, like what was happening before, your complex verification pipelines become sources of error in their own right. And the final take-home lesson is there's, of course, still a lot to do. This is very early stage for this domain. The work we have done with Vehicle and other teams have done in France is still more of a feasibility study and probably years away from a stage of verified multi-backend compiler, which would be the destination for this work. You essentially want to have an environment where you verify everything, you have a pretty and very rigorous specification language, and then you compile everything to your other backends. However, when I'm saying that it's still a feasibility study, we put some effort into this feasibility study. So Vehicle is not just a specification language. We implemented all those 3 backend compilers that you have seen and tried to formalize properly its type checking mechanism from specifications to the Marabou. And this is this paper. And currently there is a work in progress of getting proof certificates from verifiers like Marabou in order to then render them back into proof terms in your top-level language. Another thing that we had a look into is how can we prove some sort of soundness of compilation from properties into loss functions. And this turned out to be a harder problem than talking about type checking procedure of the language, but this paper in ITP this year is particularly what I'm proud of. We had to use quite complex mathematical components libraries in order to prove validity of compilation from properties to loss functions. There is this paper that I have a few copies. If you like, just take it over the coffee break or email me. We just submitted it as a position paper. But I gathered a few people who worked on implementation of neural networks, on verification, and we have tried to gather all this information that I put in a short talk together as a memo for all of us, what we could work on if we wanted to make neural net verification better. So we're looking for collaboration, feedback, any ideas how to fund this work. But I was listening to Peter's talk yesterday, and I copied over his recipe. So recipes for success of any verification project, according to him, is support and extend conventional applications. It's something that we intuitively did when we started this project. We looked exactly how machine learning people define the problem, exactly how those people who build neural net verifiers define this problem. So we try to be faithful to this. Specification is primary, documentation is, again, pretty much vehicle, and specification is primary design tool, the same. And hopefully we're also trying to clarify existing abstractions. So I was looking at it and thinking, well, we intuitively probably made pretty much same choices that Peter recommends we should have. And this is the end of my talk. We'll be very happy to hear your feedback about this. And for the Q&A session is a team of people who helped with design of the language vehicle. Thank you.